Okay, dear students, welcome back to the physics class. As you know, in the previous class we already discussed regarding the concepts which related the applications of total internal reflection, right? So in that applications of total internal reflection, I have said there are three applications. In those three applications, I discussed already the first application, that is brilliance of diamond. Now let us move towards the discussion of how the total reflecting prisms are going to work and how they are going to form the image. Dear students, you can observe that the word itself giving that we have a prism, whereas that prism is completely reflecting the incident beam of light. So you know this, that the prism is reflecting, then how that prism is exactly reflecting and what is the definition of total reflecting prism. Let us see what is the definition of total reflecting prism. Dear students, whereas thus total reflecting prisms is a total reflecting prisms are said to be an isosceles, right angled prism which reflects incident beam of light by the angle of 45 degree and even by the angle of 180 degree. Let us see that how this exactly going to reflect the rays of light when it is going to fall on the prism. See, we have two types. So already I said you that the total reflecting prisms are called as isosceles right angle prism, which is working on the principle of total internal reflection. So then, what is the refractive index of the total reflecting prism? So the total reflecting prisms is made up of glass, whereas glass is having a refractive index of n is equal to 1.5. As well as, dear students, we should know what is the critical angle. What is the critical angle for the total reflecting prisms? That is what? About 42 degree. 42 degree is the critical angle for total reflecting prism. So that to observe the total internal reflection, in case of this prism, we should incident a ray of light which is greater than this critical angle. That is what I can easily say that the angle of incidence should be greater than 42 degree. Especially I am going to note it as the angle of incidence. Angle of incidence is equal to 45 degree. When a ray of light incident at an angle greater than the critical angle, that is greater than the 42 degree, that is said to be the 45 degree, so that it reflects totally. Now let us observe, let us write the diagram for the two different cases. See, I am writing here one of the prism, so whereas here it is a right angled prism, here it is a right angled prism. So this is said to be the 90 degree, right? And other two angles are said to be 45 degree each. Said to be 45 degree each. Now I am going to incident a ray of light. From an object, so that the two rays of light are going to fall on one of the slant side of the prism. You can observe that the angle of incidence should be always greater than that of the critical angle, that is 42 degree. So here at the point of incidence I am going to draw the normal. Here also at the point of incidence I am going to draw the normal, right? See, dear students, so this is said to be 45 degree, that is angle of incidence. Here it is said to be 45 degree, that is an angle of incidence. So here already I said you that this is a total reflecting prism. So that when a ray of light incident on one of the side of an isosceles right-angled prism, so here the light ray reflects back. The light ray totally reflects. So that it reflects in this way. So it reflects in this way. You can observe that the top of an arrow, the top of the object is here, whereas the tail of an object is here. So that at first before reflection, object was like this. After reflection, the object was in this way. It means here the total reflecting prism inverted the image by 90 degree. It has inverted the image by 90 degree. Similarly, dear students, even we can observe the same case by considering 180 degree also. So I am going to write another one of the prism, whereas which is going to invert exactly the incident beam of light to 190 degree, or which is going to invert the object with the angle of 180 degree. See dear students, here again I have written the same isosceles right-angled prism, which is having 245 degrees of angle each and 190 degree, right? Now, let us allow the ray of light to fall on the what exactly the thing that prism we place here. So that now I am going to consider an object which was present here. The parallel beam of light are coming from this, right? And it is going to fall on the one side of the isosceles right-angled prism. Dear students, so you should know that for total internal reflection, the angle of incidence should be greater than the critical angle. That is here, again the angle of incidence should be greater than 42 degree. That is greater than 42. That is equal to 45 degree. Yes. Now, you can observe here. You can observe here. So that after, so here at the point of incidence, I am going to draw the normal. So at the point of incidence, I am going to draw the normal. Whereas this is the angle of incidence greater than critical angle, that is 45 degree. So after internal reflection, it falls on the another face. It falls on the another face. Right. So whereas here it again it suffers a total internal reflection at the point of incidence, and then it reflects and comes out of the prism. So that here the object is exactly inverted by an angle of 180 degree. Why? Because at first the object was like this, now the object is in this way. It means the angle in which at which the total reflecting prism inverted the image, inverted the object is equal to 180 degree. But here it is of about 90 degree. Here it is of about 90 degree. So yes, this is how the two reflecting prisms I explained over here, my dear students. So this is the mechanism how the total reflecting prisms are going to invert the object. That is what the image of an object. So and also reflects the total incident ray of light towards the same medium. So now the angle of one thing that we should note is the angle of incidence should be greater than of the critical angle. That is what equal to 45 degree. Critical angle is 42 degree. Hope you got this diagram. Yes. Now let us continue the last application of the total internal reflection. That is said to be optical fiber. So you might have heard the optical fiber in your daily lives. So we have a lot of applications with the help of optical fiber. Dear students, when we come towards optical fiber, you know so many uses of the optical fiber. First I should note the uses. So here, in case of this optical fiber, we use this optical fiber for telecommunication. Not only the telecommunication, even you might have observed in exhibitions, even you might have observed in some shops, whereas the optical fiber is used for decorative purposes, decorative lamps. So that you might have observed that the optical fibers are like thin, flexible plastics in which they are going to fall in the shape of a waterfall, whereas they are going to give a different colors, so that it is used as a decorative lamp. Yes. The next thing is this optical fiber, even it is used in the medical field, that is for observing so that is for exactly for endoscope, that is for endoscopy. So that purpose the optical fibers are used, and also to transmit the audio and video signals. To transmit audio and video signals, we use an optical fiber. See, these four applications of the optical fiber are very much essential for us in this era. So I can say that the optical, so in these days, so that this optical fiber, discussing about how the optical fiber is made of, how actually it is going to reflect the incident beam of light, is must essential. Okay, hope with this uses I am just moving towards writing out the diagram for optical fiber. Dear students, here I am just representing the optical fiber. So keep in your mind that the optical fiber is made up of a flexible glass or a plastic, right? It is made up of flexible glass or a plastic. Whereas dear students, when we come towards the optical fiber discussion, so that the optical fiber is exactly covered, it is exactly insulated. So I can say that to provide the strength and to avoid the loss of intensity of the signal, we are going to insulate the entire optical fiber with a outer core, with the outer jacket, with an outer core or insulator called as plastic. Dear students, so this optical fiber is made up of core, right? I am writing, this is a core, whereas this core is again covered with a coating called as cladding. See dear students, this optical fiber is made up of flexible glass, whereas this optical fiber is having a core and cladding. So whereas this is said to be the core, this is said to be the core, and this is said to be the cladding. Yes. Whereas the refractive index of a core is always greater than the refractive index of a cladding. Whereas to protect this entire optical fiber, this core and cladding is again covered with an insulator that is said to provide the strength and also to avoid the loss of signal and all. Remember my dear students, so this optical fiber is going to work on the principle of total internal reflection. The principle of optical fiber is that is said to be the total internal reflection. Now, if a ray of light, if a signals is going to be incident at an angle of incidence greater than the critical angle, see at the point of this incidence, so the angle of incidence is greater than the angle of critical angle, is said to be I is greater than IC. So now the ray of light reflects and falls on the next surface. Similarly, the process continues, and after a series of reflection, it comes out of the other surface. Dear students, you can observe that when the ray of light incident at the core and the cladding interface with an angle of incidence greater than the critical angle, so it undergoes a series of total internal reflection and finally comes out from the other end of the optical fiber. Whereas at the other end of the optical fiber, if you get the signals, those signals are of same intensity. There is no loss of intensity internal reflection. There is no loss of the information due to the total internal reflection, but this total internal reflection gives you to maintain the intensity or to maintain the, that is what we can may avoid the loss of signals while it is going to send the information from one end to the another end. This is how actually the construction as well as the principle and the working of the optical fiber. So hope you got the applications of total internal reflection. But the natural example is said to be mirage. So you might have all experienced this mirage. Suppose if you went to, if you go to the desert land, or suppose if you just move outside in a field or in a ground. So if you observe that the image of a tree, so it appears to be inverted and it appears to be the image formed inside the pool. So dear students, let us see that consequence here. So mirage. So let us see this one. What is mirage? Right. Dear students, now consider that I am going to write a desert land here. So right, I am going to write a desert land. So that here we have a tree. Here we have a tree, whereas observer is present at this position. Observer is present at this position. Now, it is a sunny day. So exactly we are in a desert. Right, desert means is exactly with sand. So during a sunny day, during hot time, so the air near the ground is less denser compared to the top, the air above the ground. Air above the ground. Air above the ground. It means why the air below the ground is less denser? Why? Because here at this position, at the air near to the surface, near to the sand, near to the land is very hot compared to that of the air near, above the earth's surface. So that is what air above the earth's surface is cool compared to that of the air which is near to the earth's surface. So you can observe that the air layers are hot near the earth's surface, and the air layers are cool at the upper surface. So you can observe that if it is hot, it means that heat is more, then density obviously reduces. So that the air near the ground is less denser compared to the air above the ground. So it means this medium is said to be the denser medium. This becomes a denser medium. So whereas this becomes a rarer medium. This becomes a rarer medium. Now the ray of light travels from the tree. See, actually this person used to observe. This person used to observe the tree. When he was walking and he was observing. So for him, actually the rays of light from the tree, they comes from the denser medium to rarer medium. You know that from the laws of refraction, when a ray of light travels from denser medium to rarer medium, they bends away from the normal. They bends away from the normal. Dear students, whereas this ray of light is reflected from, you can see that here, this is possible, this is from the sun. So the ray of light has been reflected from, the sun. So now if I extend this ray, so you can observe that for the person, the tree appears to be in this direction. So it means the inverted image has been formed. Not only that, here the ray of light is showing this phenomena that is due to the sun. But the ray of light is totally internally reflected due to the sun. So as well as the sand has been reflected in this way, but the sand appears in the form of pool. As well as for an observer is going to see that the tree is inverted and the image of the tree is inside the pool. Why this is? This is exactly due to the total internal reflection, and this kind of illusion is called as mirage. So mirage is said to be an optical illusion caused, the mirage is said to be an optical illusion caused due to total internal reflection, caused due to total internal reflection, right? So dear students, so hope you got this. This is why actually the person is going to observe a pool that is said to be, he actually assumes that the image of a tree is formed inside the pool at a large distance, very far away from the person. The optical illusion is observed by the person called as mirage. Hope you got this? Yes. Okay. This is about some of the concepts related to the total internal reflection, my dear students. Now, dear students, now let us move towards the discussion of refracting surfaces. Exactly, I am saying you that the spherical refracting surfaces. So you might have studied the spherical reflecting surfaces in your 10th standard. So but now I am discussing the spherical refracting surfaces. When we come towards the spherical refracting surfaces, there are two types. There are two different types. One is a convex spherical refracting surface. Another one is concave spherical refracting surface. See, we have two types. One is convex and concave. Before going towards the discussion of convex and the concave, and also the terminologies which comes under the spherical refracting surface, let us define what is spherical refracting surface. Dear students, spherical refracting surface is a surface in which it is a part of a sphere. The part of a sphere. See, if I just write a sphere here, so I am just writing a sphere. So I am just writing a sphere here, right? So you can observe that the sphere is exactly present here. The part of a sphere which refracts the incident beam of light is called as spherical refracting surface. I am repeating again, the part of a sphere, that which refracts the incident beam of light is called as a spherical refracting surface. Dear students, in this I have already said you that we have two types. One is convex and another one is concave. Okay, now I am going to write the two diagrams which exactly gives you the difference between the convex and concave spherical refracting surfaces. Dear students, so that I am just writing it here. Observe carefully. So I have written two surfaces. See, dear students, the refracting surface which is convex towards the rarer medium. So this is the rarer medium, whereas this is said to be the denser medium. So that the surface which is convex towards the rarer medium is called as convex spherical refracting surface. And you can observe here the surface, here it is, this one is said to be the rarer and this one is said to be the denser medium. So that the surface which is concave towards the rarer medium is called as concave spherical refracting surface. Okay, so here we have two types. I just written the different diagrams for both the convex and concave. For both the concave and the convex to define, but we should know some of the terminologies which comes in this spherical reflecting surface. Terminologies. Okay, some of the terminologies which comes in this. Okay, the first thing is center of curvature. Okay, let us define what is center of curvature. You can observe here, students, this is center of a sphere, whereas here it is also a center of a sphere. See that center of curvature is the center of a sphere in which the spherical refracting surface forms a path. Why? Because spherical refracting surface is also having the same center. Similarly, the sphere is also having the same center. So that I can easily define center of curvature is the center of this entire sphere in which the refracting surface forms a path. Whether it may be the convex or whether it may be the concave refracting surface. Center of curvature is represented by the symbol C. And now let us move to the next terminologies that is said to be the principal focus. Principal axis. Principal axis. Dear students, so if I just draw the line, you can observe that. So this is said to be the diameter, let me say. Yes. If I draw the line like this, so you can observe that it is a midpoint of the refracting surface represented by P. It is a midpoint of the refracting surface represented by P. What is P? P is said to be the pole. Dear students, pole is represented by the symbol capital P. So that pole is the center of a refracting surface. So P is a point. P is a point lying on the principal axis. And pole is the midpoint, is exactly the midpoint for the spherical refracting surface, and it is represented by capital P. What is the principal axis? The line which is passing through pole and the center of curvature of a spherical refracting surface is called as principal axis. So this line is called as the principal axis. It can be written as E or principal axis, right? Now, the distance between the pole and the center of curvature is called as radius of curvature. Radius of curvature, represented by the symbol capital R. What is the radius of curvature? Radius of curvature is the distance between pole and the center of curvature. Dear students, so even we have a focus, principal focus in case of this convex refracting surface as well as in case of concave refracting surface. And also we have focal length, so that I will discuss it in the next. So that is what, while deriving the equations, I will just show you how to define the focal length as well as the principal focus just by writing out the ray diagrams. Now I just explain you the radius of curvature, so that with the help of these all the terminologies, even we can define the refracting surface. So that the refracting surface, so this is said to be the refracting surface. I am going to give the name as XY. Here we have this as the refracting surface, so I am going to give the name as XY. So that the part of a sphere which refracts the incident beam of light is called as aperture. Whereas aperture is represented by the symbol capital A. So my dear students, so these are the terminologies related to the convex and the concave refracting surfaces. Yes. Now let us see the sign conventions related to this refracting surfaces. Right. Let us see the sign conventions related to this. Conventions. So hope you are all taking down the points and what I am explaining here. So don't forget to take down the points, dear students. See, the first point is the distances, all the distances should be measured from the pole. All distances are measured from the pole along the principal axis. So that is said to be the first sign convention. It means if you want to measure the object distance, we should measure from pole itself. As pole as a reference point, we should consider pole as a reference point, and then we should measure other distances. If I want to measure the radius of curvature, from the pole only I should measure. If I want to measure the I want to measure the object and the image distances. See, this was the first sign convention. So just remember that. Assume that the object is here now. The object is here. So the ray of light is going to incident in this direction. So so here exactly after refraction, my dear students, after refraction, the ray of light is traveling from rarer to denser medium. So after refraction, it shifts towards the normal and forms an image at this position. Right, dear students, the distance between the pole and the object is called as object distance, represented by the symbol small u. And the distance between the pole and the image is called as the image distance, represented by the symbol v. Now, how to measure this with the help of sign convention? See, if I want to measure object distance, I just use pole as the reference point, and to measure the radius of curvature, I just consider pole as the reference point, and to measure the image distance, I consider pole as a reference point. So for all the distances, I considered pole as a reference point, and I measured all the distance along principal axis. Next sign convention is distances measured along all the distances measured along the direction of incident ray, along the direction of incident ray is positive, is taken as positive, otherwise it is taken as negative. I am repeating again, the distances which are measured along the direction of incident ray. How to observe that? See, actually the object is here. Incident ray is moving in this direction. It means the incident ray is from here to here. The incident ray is from here to here. Right? Hope you are getting the direction of incident ray. I am just showing the direction of incident ray. This is the direction of incident ray. According to the sign convention, we should measure the distances along the direction of incident ray. The distances are taken as positive. If the distances which are measured, opposite to the direction of incident ray is taken as negative. Now the incident ray direction is thus. No problem. I want to measure the object distance, write it as u. I want to measure the image distance, write it as v. I want to measure the radius of curvature, write it as r. So by using these two conventions, see here, so that the object distance is measured from pole to this direction. It means I am measuring the distance, I am measuring the opposite object distance opposite to the direction of incident ray. Incident ray is in this direction, whereas my measurement is in the opposite direction, so that the object distance is taken as negative. Similarly, the image distance is measured along the direction of incident ray. Radius of curvature is measured along the direction of incident ray, so that it becomes positive. So this is how to just apply the sign conventions. Keep in your mind, there are 3 sign conventions. These 3 sign conventions are very much essential so that to solve the derivations. Okay, now the next part is, now let us deduce the expression which relates refractive index, object distance, image distance and radius of curvature for spherical refracting surface. Write it as spherical refracting surface, don't write it as SRS. So dear students, now I am just going to consider convex spherical refracting surface. Right? So whereas the convex surface is towards a rarer medium, so I am just going to extend this to get a complete sphere. Right? To get a complete sphere. So So this aperture is given by the name xy. So whereas the center of the sphere is C, center of the sphere is C, whereas the pole is represented by capital P. The line which is passing through the center of curvature and the pole is considered as the principal axis, right? Now I am going to write the distance between the pole and the center of curvature called as the radius of curvature. Let us consider an object which was present at this position, give the name as O. Then the distance between the pole and the object is called as the object distance, represented by U. From the object, ray of light is going to incident, so that the ray of light is going to incident on the spherical refracting surface. So you can observe that at the point of incidence, at the refracting surface. So I am just going to draw the normal. The normal is passing through the center of curvature. Yes. Whereas the angle which is present between the normal and the incident ray is called as angle of incidence I. So whereas the ray of light is traveling from rarer medium to denser medium, denser medium, so that the ray of light bends towards the normal with an angle of refraction R, right? And finally it is going to form an image I at this position. Then dear students, the distance between the pole and the image, is called as the image distance, represented by V. And one thing, so you can observe, to derive and to explain the situation, I am just going to consider these angles, so that the angle which is present between the principal axis and the incident ray is considered as alpha, and the angle which is present between the refracted ray and the principal is considered as beta, and finally the angle which is present between the principal axis and this normal is considered as gamma. Right. See my dear students, this is about the diagram and this is about how the refraction takes place in case of the refracting surface, convex refracting surface. And see here, let us note it down. OP is equal to U, PC is equal to R, PI is equal to V. Let us note it down. So that OP is equal to U, right? OP is equal to U and PC is equal to R from the diagram, and PI is equal to V. PI is equal to V, right? Not only that, even you can observe here this is said to be the normal, right? Here it is said to be the normal, as well as the angle. See, I am just writing here as N. So that NOP is equal to alpha, right? I am writing here NOP is equal to alpha, and similarly NCP is equal to gamma, and the remaining is NIP is equal to beta. So just I explained the diagram. So dear students, hope you got the diagram and how what I written on the board. So just to go through the diagram once clearly. So in the next class let us move towards deriving this expression, right? So one thing, so write the diagrams with the help of pencil. Don't use a pen to write the diagram. And here while representing the rarer and the denser medium, please be careful that the rarer medium is always considered as an air medium and denser medium is a glass medium with a refractive index N. So in the next class we can move for the derivation of relationship between N, U, P and R. Thank you.